Potential energy is the energy associated with the position or configuration of a system. It is not associated with motion as with kinetic energy. The forces involved can be conservative or non-conservative. With a conservative force, the path taken going from point A to point B doesn't matter. So it doesn't matter if you go from A to B like that, or like that. The work done is the same for all paths. Also, if you go to A to B and then back to A again, the results will be no net work. In other words, the energy of a conservative force can undergo transformation but is not lost. Examples of a conservative force are gravity, a spring, or even a pendulum. A non-conservative force produces a type of energy that can't be recovered or changed to another form. Examples of a non-conservative force would be friction, which results in thermal energy, and drag. For conservative forces, the change in potential energy is given by delta U equals minus W. It is negative of the work done. So for example, if you throw a rock up in the air, the potential energy increases because the rock gains height, but the work done is negative because the work is acting against the motion, which is upwards. If the rock falls back down, the potential energy decreases because the height is decreasing, and the work is positive because gravity is working in the same direction as the motion. So we know that work is equal to the integral of fx dx. Then, putting that into this equation here, we end up with the change in potential energy is equal to minus the integral of fx dx from point 1 to point 2. Or we can write that as fx is equal to minus derivative of the potential energy dx. Now let's look at a specific system, namely gravity. So in gravity, the force, well, in this case is y, is equal to minus mg. So if we substitute that into this equation here for potential energy, we get potential energy of gravity is equal to minus the integral of minus mg dx. I'm sorry, that would be dy, because we're in the y axis. So the change in potential energy for gravity is equal to mg change in y. And if we start with y0, our reference point, equal to 0, we get the potential energy as a function of y is equal to mg times y, which is the height. Let's look at an elastic system, namely a spring. Well, we know the force of a spring is equal to minus kx. So again, substituting that in for our potential energy equation, we get delta U is equal to minus W, which is equal to minus the integral of minus kx dx. Or delta U becomes 1/2 k x final squared minus x initial squared. And again, if we cause the reference point to be 0 for the initial x, we get potential energy of a spring is equal to 1/2 kx squared, which is also the elastic potential energy. So if we take a spring that's at rest here and we stretch it, its potential energy increases, but the work done by it decreases because the spring's force is acting opposite of the direction that we're stretching it. If we then allow that spring to relax and move back towards its relaxed point, then its potential energy decreases and the work it does is positive because the force of the spring is now working in the direction of the spring motion. Now we're going to talk about conservation of mechanical energy. When we say mechanical energy, we're mainly talking about kinetic energy and potential energy. And we're also going to assume that all forces are conservative and there's no external forces acting. So basically, mechanical energy is equal to kinetic plus potential energy, and that remains constant. Energy cannot be created or destroyed. It can only be transformed. So as kinetic energy goes up, potential energy has to go down, and vice versa. So what we get is any change in kinetic energy is equal to a minus change in potential energy. So we can write that E mechanical is equal to the change in kinetic energy plus any change in potential energy, and that is 0. We can use this to solve many problems that are difficult to solve with Newton's laws. So basically, you can look at a system and you can look at its initial and final states and solve problems, and you can ignore anything that goes on between these two states. We don't care about necessarily how the velocity has changed or its momentum. We just need to worry about the initial and final states. So we had seen that work is equal to the change in energy, and let's talk about mechanical energy at this time, which is equal to the change in kinetic energy plus the change in potential energy. But what if we have friction? In this case, work is equal to the change in the mechanical energy plus the change in the thermal energy. And we call it thermal because friction leads to heat, which becomes the thermal energy. And we can also say that this change in thermal energy is equal to the force of friction times the distance the friction moves an object. So let's talk about conservation of energy when we talk about external forces and friction. So we're going to add external forces and friction now. So in this case, the work done is equal to the change in the total energy, which is equal to the change in the mechanical energy plus the change in the thermal energy plus the change in internal energy, which internal energy will be any change in the system due to other forces. So if we have an isolated system, which means no energy can be transferred to or from the system, then the energy stays constant and the change in energy is zero. Therefore, our work is zero. And from this equation, then, we find that the change in mechanical energy plus the change in thermal energy plus the change in internal energy is equal to zero. And if we call the mechanical energy the change mechanical 2 minus mechanical 1, we then can get our final mechanical energy is equal to initial mechanical energy minus change in thermal energy minus the change in internal energies. Before we do problems using conservation of energy, let's review a few points. Using conservation of energy allows us to look mainly at the initial and final energy states of a system to solve problems. If we have conservative forces with no friction, then the laws of conservation of energy state that the total final energy equals the total initial energy. If we add friction, then the total final energy is equal to the initial mechanical energy plus whatever work was done by friction. And if we have other internal forces, then the total final energy will equal our initial mechanical energy plus the work of friction plus the work of the internal forces. Now let's do some problems. A mass is attached to a 10-meter cord, making a pendulum that swings from rest, starting at a point 60 degrees to the left of vertical, through the lowest point to a point 30 degrees to the right of vertical. What is the speed at its lowest point? What is the speed at the point on the right? Okay, well, let's make this a little easier and diagram this. So we have a pendulum and it swings and it starts at a point 60 degrees to the left and it goes to a point 30 degrees to the right. And it's moving in this direction. We'll call this point A and point B. And we'll call this the initial point. So we have to have a reference frame, and we'll call the bottommost point x equals 0. And this is the length of the cord, radius is equal to 10 meters. And we're assuming there's no friction because we're ignoring air friction. So let's write our conservation of energy law. We're looking for the velocity at point A. So the energy at point A is equal to the energy at the initial point. So as we fill this in, we get 1/2 mVA squared, and because it's at the lowest point, its potential energy is 0, is equal to, well, the kinetic energy where it starts, it's at rest, that's 0, plus mg. Now we have to find h, and we will do that in a minute. So basically we can cross out the masses, and we get 1/2 VA squared is equal to GH, or VA ends up being the square root of 2GH. Okay, so how are we going to find H? Well, if we redraw that, here's 0, this is H, this is R, this is 60 degrees. This distance is R cosine 60 degrees. So R is equal to R cosine 60 degrees plus H, or H is equal to R minus R cosine 60 degrees. H is equal to, we know R is 10 minus 10 times 0.5, and if we do that calculation, we find H is equal to 5 meters. So then if we go back to equation 1 and substitute what we know, we get velocity at A is equal to the square root of 2 times 9.81 times H, which is 5. So that's equal to the square root of 98.1, or the velocity at A is equal to 9.9 meters per second. Now for part B of the question, it wants to know what is the velocity at point B, where the pendulum is swinging through. Well, we could use the starting kinetic energy as that being at point A, but let's use the initial point because that's a little bit easier. So once again, the kinetic energy at point B plus its potential energy is equal to kinetic energy initial plus potential energy initial. So if we go through this again, we get 1/2 mVB squared plus, now in this case, we do have a potential energy because B is at a height above x equals 0. We'll call that H prime. So the potential energy at B is mg H prime is equal to 0 plus mgh. And we can cross out mass, and we end up with VB squared is equal to 2g h minus h prime, or VB is equal to the square root of 2g h minus h prime. So now we need to find h prime. Well, in this case, this is 30 degrees. This is h prime. And this is r cosine 30 degrees because the angle is 30 degrees. So similar to part 1, we know that r is equal to h prime plus r cosine 30 degrees. H prime is equal to r minus r cosine 30 degrees. H prime is equal to 10 minus 10 times 0.87. And if you follow this through, H prime is equal to 1.3 meters. So now putting that into equation 2, we get VB is equal to the square root of 2 times 9.81 times h, which we know is 5, minus h prime, which is 1.3. VB is the square root of 72.6, or VB is equal to 8.5 meters per second as it passes through point B in the arc. A boy starts from rest at the top of a quarter circle slide with a radius of 20 meters. At the bottom, call this point A, he slides out onto a flat surface and comes to rest at a point B on this surface. Assume no friction on the circular slide, but there is friction on the flat surface with a coefficient of friction of 0.25. What is his speed at point A? What is the distance between point A and point B where he stops? So let's diagram this. We have a circular slide, and then at point A it becomes a flat surface, and this has a radius of 20 meters, and note that that's the same at point A. We'll call this his initial point, and where he stops is point B, and we want to know the distance to point B. There's no friction here, and there is friction here with a coefficient of friction equal to 0.25, and we'll take our 0 reference point to be at the surface here. So we want to know, first of all, what is the velocity at point A? So let's write our conservation of energy formula. Final kinetic energy plus potential energy is equal to initial kinetic energy plus initial potential energy. Since there's no friction, it's all mechanical energy. So let's put in the values. 1/2 mVA squared plus 0. There's no potential energy at A because it's our 0 reference point, is equal to 0 kinetic energy because it starts from rest, plus mg times height. And in this case, the height is equal to the radius. So we can cross out the masses, and we end up with VA squared is equal to 2 times the height times g. VA squared is equal to 2 times 20 times 9.8. VA squared is equal to 392, or the velocity at A is equal to the square root of 392, which is equal to 19.8 meters per second. That's the velocity at the bottom of the circular slide. Now we want to find the distance between A and B. And in this case, there is friction. So let's set that up. So in this case, kinetic energy at B plus potential energy at B is equal to kinetic energy initial plus potential energy initial plus the work done by friction. Now, at B, he has stopped, so there's no kinetic energy, and he's at the 0 reference point, so there's no potential energy. So 0 plus 0 is equal to, okay, again, he started from rest, so his kinetic energy initially is 0, plus mgh, which was the radius. And in this case, the work done by friction, because it's going opposite the motion, is a minus coefficient of friction, normal force, times d. the distance we're looking for. So we end up with mgh is equal to mu normal force times d. Now, what's the normal force? If we go back up here, the boy is sliding. We have a normal force and his weight. And because there's no motion in the y-axis, we know that the normal force must equal the weight. So if we plug that in, we get mgh is equal to mu times the normal force, which is mg times d. We can cross out mass, cross out g, and we get d is equal to height over mu, which in this case is 20 meters over 0.25, or the distance he slides is equal to 80 meters. Here's another problem. A roller coaster with a mass of 200 kilograms slides from rest at the top of the ride down the track, goes through a 360-degree loop, then continues horizontally. The loop has a radius of 20 meters. Assuming no friction, what is the minimum height needed for the coaster to make it safely through the loop? Once again, we're going to draw this. So we have coaster coming down, goes through a loop, and continues horizontally. We know that the radius is 20 meters. And the coaster starts up here. It's 200 kilograms. We'll call that the initial point. And our axes, x0 will be at the bottom of the loop. And we'll call this height hi, the initial height. And we want to know what's going on at the top of the loop. And we're assuming no friction. So for the coaster to make it around the loop safely, that actually means that the normal force has to be positive. That means that the coaster is in contact with the track. If the normal force was 0 or negative, that means that the coaster had no contact with the track and it could fall off. So we need the normal force to be greater than 0. So let's look at that normal force. If this is the loop, we have the weight of the coaster, mg, and we have the normal force, Fn. Okay. And note that the weight and Fn are centripetal forces. And if we use Newton's second law, we find that Fn plus the weight is equal to the mass times the centripetal acceleration. Or Fn is equal to mass times centripetal acceleration minus g. So we had said that we need the normal force to be greater than 0. So for that to happen, the occipital we also know that centripetal acceleration is equal to v squared over r. So that would have to be greater than gravity constant, or v squared would have to be greater than rg. So this is the requirement for the velocity for the coaster to go through the loop safely. Now let's go back to our conservation of energy law and look at the final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy. And there's no friction, so we're just looking at mechanical energies. So at the top of the loop, which is where we're looking at these energies, we have 1/2 mv squared plus mg times the height is equal to initial kinetic energy is 0 because it started from rest, plus mgh initial. And this is what we're looking for, what the initial height has to be to make it through the loop safely. So we can cancel out the masses, and we get 1/2 v squared plus gh is equal to ghi. And we know that, if we go back up here, that this height is equal to twice the radius. So this becomes 1/2 v squared is equal to plus g times 2r is equal to g times the initial height. So if we write ghi is equal to v squared over 2 plus 2gr. Now, we previously found from this that v squared has to be greater than rg. So if we plug that back into this equation, ghi has to be greater than, v squared has to be greater than rg over 2 plus 2gr. We can now get rid of the constants of gravity and get h, and height has to be greater than r over 2 plus 2r, or the initial height has to be greater than 2.5 r, and since r is 20, initial height has to be greater than 50 meters. That's how high the roller coaster will have to start at to make it through the loop safely. And notice that it doesn't depend upon mass. Let's do a spring problem. A spring has a coefficient of 75 newtons per meter. Its left end is fixed and its right end has a mass of 4 kilograms attached to it. Assume no friction. The spring is compressed 5 meters from its relaxed position and then released. What is the speed of the mass when it passes through the relaxed position of the spring? So let's draw this. We start with a spring and a mass, and we compress the spring. So this is the relaxed position, this is the compressed position. And we're going to take the initial position as the compressed position, so we'll call that XO. But its actual relaxed position we'll call X. And the mass is 4 kilograms. The spring coefficient is 75 newtons per meter. And we're assuming no friction. And we want to know what is the speed when it is released and it passes back through its initial relaxed position. And the potential energy of a spring, as we know, is given by 1/2 kx squared in general. So let's look at the conservation of energy equation. Final kinetic energy plus final potential energy equals initial kinetic energy plus initial potential energy. So again, we're taking the initial position to be at the compressed point, x0. So we'll start there. Since it's starting at rest at that point, its kinetic energy is 0, but its potential energy is 1/2 k x0 squared. Looking at the final energies as it passes through x, we know that its kinetic energy is 1/2 m times the velocity of x squared as the kinetic energy, but its potential energy is 0 because it's at its relaxed point, and at its relaxed position a spring has no potential energy. So continuing the equation, 1/2 mvx squared is equal to 1/2 kxo squared, or mvx squared is equal to kxo squared. Vx squared is equal to kxo squared over m, or Vx is equal to xo times the square root of k over m. And we know these amounts. Xo is the amount of compression, 5 meters, is times the square root of k, which is 75, over the mass, which is 4. So Vx is equal to 5 times the square root of 18.8, or Vx is equal to 5 times 4.3, or the velocity as it passes back through its equilibrium point is 21.7 meters per second. Let's do a problem related to power. A conveyor belt lifts cargo to a height of 10 meters, at which point it is discharged through a chute at a rate of 2 kilograms per second and a velocity of 3 meters per second. What is the minimum horsepower that is needed to unload the cargo using this setup? Okay, so once again we're going to diagram this problem. We have a conveyor belt going up to a height of 10 meters, and it's discharging cargo through a chute at 2 kilograms per second and a velocity of 3 meters per second. So we want to know what the horsepower is needed. So we know that power is equal to the change in energy over time, which would be change in kinetic energy plus change in potential energy over time. So that would be equal to mgh plus 1/2 mv squared over time. And we're assuming that time in this case is 1 second. So that means that our power is going to be mgh plus 1/2 mv squared, and we know this amount, so that's 2 times 9.81 times height of 10 meters plus 1/2, 2 times velocity, which is 3 squared. So that is equal to 196.2 plus 9, or 205.2 watts. But it's asking what the horsepower is. So we know that there is 1 horsepower per 746 watts. So we multiply that and we get 0.28 horsepower. That's what it would take for this conveyor belt to discharge a cargo as shown. Let's do one more power problem. How much power would a man expend in dragging a 100 kilogram crate down a hill at a speed of 1 meters per second? The hill is at a 20-degree angle with the horizontal. The coefficient of friction between the crate and the hill is 0.9. So if we diagram this, we have a hill, 20-degree angle. We'll call this height h. We have the crate going downhill, and we'll call that a distance d, and it's going at a velocity of 1 meters per second. So if we look at our free body diagram, we have the weight, we have the normal force, and we have friction, and that's 20 degrees. We also know that the coefficient of friction is 0.9 and the mass is 100 kilograms, the crate. So we want to know what the power would be that the man would expend. And in general, power is the change in energy over time. So the change in energy is basically equal to the change in kinetic energy plus the change in potential energy, which in this case is due to work done by friction plus the work done by the man. So we want to find out what the work done by the man is. Okay, so that's equal to change in kinetic energy plus change in potential energy minus the work done by friction. This is zero because it's moving at a constant velocity. The velocity at the top and the velocity at the bottom is the same, so the change in kinetic energy is zero. So the work of the man becomes the final potential energy minus the initial potential energy minus the work of friction. Well, the final potential energy is zero because it's at the bottom of the hill. So it's zero minus the initial potential energy is mg times h, this height, and minus the work done by friction. Well, the work done by friction is minus umg times d cosine 20 degrees. So the work of the man becomes minus mgh plus coefficient of friction mg, the distance it travels down the hill, cosine 20 degrees. Well, h we can get from this angle. H is simply d, distance it travels, times sine theta, which in this case is 20 degrees. So that's equal to mg, distance, sine 20 degrees. And we don't know the distance that it travels down the hill. Let me just finish this equation. Well, we know velocity is distance over time. So we know the velocity that it's coming down the hill. So d would simply be velocity times time. So if we substitute that in, we get mg, velocity times time, sine 20 degrees. It's minus plus mu mg vt cosine 20 degrees. Okay, now power is equal to the work done over time. We've seen that before. So that would be equal to this whole equation divided by time. So we can cancel this out and we end up with power equal to minus mgv sine 20 plus mu mg v cosine 20 degrees, which is equal to mgv, if we take this out of both equations, times mu cosine 20 minus sine 20 degrees. Okay, I reversed the minus sign. And we know these amounts. So that's equal to 100 times 9.81 times the velocity, which is 1 meters per second, times 0.9 times the cosine of 20 is 0.94 minus the sine of 20 is 0.34. So that equals 981 times 0.85 minus 0.34, or 981 times 0.51, or it's equal to 500 watts. That's the power of the man